Hi, folks. I'm Julian Doherty. I was going to do this like huge talk. It was at work. I work at a company called Sendle, and kind of one of the things we do internal talks similar to this was about how scheduling and concurrency works inside the Beam VM. So I was going to put something together for that, and I thought, hey, it'd be really cool to like build almost like a mini toy scheduler, doing like basically could run some really basic instructions and do stuff. And that would be awesome. It'd be a really good way to show it off. It ended up being like really complicated to do. And it's not actually that complicated, but kind of all the steps to get along the way are complicated. The first step is actually understanding what the bytecode happens. So when you have like some Elixir code that gets compiled and you run it, how does that get turned into something that the Beam will actually run? I kind of got to that bit, and that's sort of what this talk is about. So there might be a follow-up probably at some point going into here's how it actually runs that stuff. But this is kind of just a bit of a deep dive into how it actually, like when Elixir runs Elixir C, like the compiler, and it spits out like a file that the VM will run. What does that actually look like? What's in that file? What does it do? So yeah, like if you actually want to look at this stuff, there's a heap of tools in, they're pretty much all in the Erlang standard library, but Elixir being Elixir, you can still call that. So if you want to do some of the stuff, dig into one of these things here. So let's say we've got some really basic code that looks sort of like that there. So really, this is my usual toy example, just doing a Fibonacci sequence. So if you haven't seen this code before, you know Fibonacci sequence, you get 0 and then 1, you get 2, and then you get 3, and then 5 and 8 and 13 and so on. And that's cool, that'll run. So it's just a simple naive recursive version of that. So if we do like fib 10, 1, it'll give us 1, 2 gives us 2, 3, another dot, and sequence as you expect. This is kind of a really fun property, this example here, because it's really simple code, but you can like cripple pretty much any hardware you're going to throw at the A version. Like if you're at 20, it's cool, 30 is cool, 40 for a bit. 50, I'm not going to do that because we'll be here. And you get up to 100, it's like the length of the universe for this to run. So as an example for code to look at, it's actually really kind of fun. So we want to take that. There's some stuff built in where you can do this in Erlang. So if you haven't seen that syntax before, we have like a colon in front of the module name. That means you're calling Erlang code rather than Elixir code. So it's exactly the same under the hood, same bytecode. You can call it transparently and get the same thing. In this case here, there's a built-in library for dealing with code, which is code. And it'll give you a bunch of helpers. One of them is get the object code for a thing. So we've defined don't do that, a fib module up here. Call this, and we'll actually get what that looks like under the hood as a binary. So that's the module name. That's where it's defined because it's compiled it in Livebooks, put it there. And this big thing here is a chunk of binary data that you can't do much with on its own. But once you pull that out, you can. So we've got this fib mod binary thing, which is literally just a big chunk of bytes that are all the serialized instructions that things can do. Got this other module in Erlang called Beam this ASM, and it's got a file function on it. Pass the binary into it, and it'll give you this output of what the like the internal stuff of that is. And you look at this, and it's kind of not that intelligible. There's a lot of stuff going on in here. Like there's sort of some things at the top, function definitions or something. There's some attributes. This is like a function with some stuff going on. So that was kind of like looking into this here. It's like, well, okay, how can you make that a bit more intelligible? So playing around with Livebook is really cool. You can use Kino, which is one of the built-in, it's not built in, but it's like one of the core kind of things you use in Livebook. You can have Kino, which is basically a way for doing graphical or, you know, better formatted, nicer, interactive animations and graphs and all that cool stuff. But it's got a bunch of stuff we can build on it as well. So I thought, okay, well, we can take that and then take this output here, which is really kind of clunky and hard to understand, and then actually have something that'll generate the output of that. So let's take our fib module there, pass it into a Beam, just the same Beam. We've just got a function on there, run that, and that'll give you like equivalent output to what was above, but it's nicer. And this makes it much easier to figure out what's going on with it. So here's all the functions that it's defined in our fib module. So we've got a fib1, and that's the only function we have for that one, actually. So I've got here that, that's the equivalent of that down to, to there. So basically the same, but easier to read. So it's kind of cool to dig into what the stuff actually means. So in this one, we've only got one function. It's called fib. First thing, it's got like an annotation saying whereabouts in the file it is. For our purposes, it kind of matches up. It kind of doesn't, because it's actually talking about Elixir will compile it down to like a kind of really minimal Erlang format first, and it's referring to the lines in that thing, because that minimal Erlang syntax tree is what actually gets compiled. It's not the raw Elixir code. Okay, so then we have label, this thing here, label 10. Anywhere in label, that's basically a jump target. So the bytecode that it runs on, it's very low level, almost like assembly, like it's bytecode. So if you've worked with Java or anything like that, similar to that, it's like a couple of steps up from assembly. So you don't have any if statements or else or any while loops or any kind of high level structures like that. Everything is just registers. There's a stack, there's a heap, and you can have jump targets where you can do a go-to. And everything is built in terms of that. So if you want to have like an if statement, it'll do a test, and then it'll have like a jump of where to go to if that test fails. If you want to call a function, it'll like be going to one of these labels as well. It can do that. There's a few other ways of doing it. But yeah, so that they're saying, okay, we've got label 10. That's a place where you can jump to if you want to. And all these things will have the second line here, which is function info. And that's just saying this is the name of, it's the module it's defined in is the fib. And name of the function is also fib. It takes one argument. And if it executes this line here, it actually crashes. And that's kind of by design. So what'll happen when this runs is that it doesn't start here. It'll have like another annotation above that's left out saying, actually jump to here. That's where you start from. And then there'll be a bunch of things. If they raise an error in the file, it'll jump back to here. So if you have a bad match or something like that, it'll jump back to that one, and that's how it'll raise an error. Okay, so the first thing it does is we're going to do a select value. What are we doing a select value from? We're going to grab it from this location here. And you'll see X's and Y's all the way through here. So anytime you see an X in a number, it's a register. So if you think of CPUs, they have a bunch of registers that are labeled. This is like a virtual machine. So the registers are literally just numbered from 0 to 1000 or 999, I think. They're logically equivalent to CPU registers, but they're not literally CPU registers. I'll kind of have some high level stuff mapping them in there, but they work the same way. So anytime you call a function, everything is done by assigning the arguments to the function to like register 0, 1, 2, 3. They'll be the positions of arguments you pass into a function. And then the return value from a function will be just put into register 0 again. So you got to read and write registers to do anything. You don't call functions with arguments. You set registers. You say run this code, and then you read the value out of the 0 register to get the output. Anytime you have an if, that's like a, don't know why they used if, but that means a go-to. So it's saying go to one of these green things. So I put them both in green, so it makes a bit more sense. So F13 means go to there, label 13. The reason why it's doing that is saying select val. It's going to examine what's in the first register, which is the first argument of this function, so parameter 1, and check if it's one of these things. Is it integer 0? Go to 12. Is it integer 1? Go to 12. And that pretty much matches up with what we have up here. So we have our two options at the start. So if we've got 0, we'll return 0. If we've got 1, we'll return 1. Which is pretty much what this is saying. So it says if it's 0, go to 12. If it's 1, go to 12. The thing that's in position in the X register, like the first argument, that is actually what we want to return in those cases. So it doesn't need to do anything there. It just says, okay, there's a value in register 0, just return it. Done. So 0 case and 1 case are handled. Then we've got the more complicated ones after that. So the ones you see all the time are BIF and GCBIF. So BIF just means built-in function. So that's all the stuff, like in this case, it's minus. It's literally saying subtract two numbers together. BIF is other ones as well. GCBIF just means it could potentially allocate memory and it might need to trigger a garbage collection. BIF, I think, is safe and it's not going to do that. Then it's got a few other things. It's got our F again, which is like a label saying we're going to jump to somewhere. And the reason it does this is if that binary function fails or if it needs to allocate memory and it can't, that's where it goes to. F0 doesn't exist. That's not a label. It says this just crashes. So we're out of memory, crash. That one there, I think, is one, I think, meaning it just is going to need to retain one register, I think. So when it does a garbage collection, make sure the value in X0 doesn't get touched. So the VM's free to move that around. So when it does a garbage collection, it might say, well, we've got 5 registers that are allocated. You can garbage collect and you can use those registers, but just make sure you copy the memory back into it when it's done. In this case, we just need 1 because our X0 is where the value is. Okay, cool. And then to the minus function, we're going to pass the thing that's in 0, 1, X0, sorry, and 2, and we're going to put the output into X1, and that there corresponds with this here, where we're saying grab the value in, take 1 away. For some reason, it's optimized it and it's done that -1 first. Probably because, yeah, I'm not sure why that is. It's kind of free to rearrange things as it wants. Actually, no, sorry, I'm talking crap. It does do the 2 first. So it's grabbing the input argument, which is our n, take 2 away from it, put the answer into register 1. Then it does an allocate, which is saying put some stuff on the heap because we need to track this data. Oh no, sorry, that's the stack. Then it does some moving around. So we've got the stuff, pull the thing that's in register X0, so that's the first argument, put it into Y0. This is the stack. So if you're familiar with how most programs or most languages will have like function calls, you'll have a stack of like a stack frame where saying, okay, this is the arguments we're putting in the stack, do some work, it's got its own memory space, and then that can have multiple stacks if you're doing recursive calls, and then it'll pop those stacks back down again when it's finished. Y is a stack value. So everything that's Y is a stack. X is a register, and then other things that are heap allocated will be, they can be allocated on the heap, but there'll be a pointer from one of those to the heap, which is a separate memory space. And then, yeah, doing some other rearranging, grab the value that's in this X1, which is we put here from doing our minus. So the value of n -2, grab that, put it into 0 position. Then when it's in 0 position, we can call fib again recursively. So we're saying, okay, we're going to call fib, and it takes 1 argument. And so when we call this, we don't actually pass in any arguments to it, because what it's doing is it says, here's the thing that's in X0, here's the thing that's in X1, just call it again, and then the things that are in there, that's what you use. You just get those things. Then we've got another built-in function where it does a minus, doing the -1, it does some moves, and then at the end it's doing a plus here, then it does the deallocate. So it's actually a really simple code that has been generated off this code here, which is also very simple. But the reason why it runs so bad is like this here is doing like, for every time you call Fibonacci, of every time you call fib, it's going to do 2 more calls to fib. So it gets, you know, exponentially worse and worse the bigger those numbers get. So yeah, a better way of doing that is something like this, where here's a memoized version of the same thing. So instead of like doing a brute force recursive call every time, so we want to get the Fibonacci value of a large number, you want to get the one below that and the one below that. Instead of just calculating that from scratch every single time, we just have a hash map where we keep track of what those answers are here, and then we can maintain that. And if we've looked up that thing before, use that value, don't have to go all the way back to the beginning to do it again. So this one here, we can run that, and that will be better. So when we ran it before, 40 would take a noticeable amount of time. This one's instant. Big numbers are instant. It just works because it's doing it in linear time. So instead of doing trillions of operations, it's doing 200. So it's much, much faster, obviously. But what does the code look like for this one? It's going to be a little bit different again. And yeah, so we can run that to get the output of that. I'm not going to go through all of it. It's pretty similar. So we've got the fib here, where it's doing that call. This is just like the placeholder function at the top, because we've got one here that kicks it off, a fib. And then we've got the fib with memo, which is what it does the actual work. That kind of keeps track of like a map to do the lookup and reading values from that and putting it back in there if it needs to. So the second part of that is a bit more stuff going on in there. So this one's actually pretty long compared to the other ones. And yeah, we've got a number of steps in there. So there's a few more things going on in there. Some of the interesting ones is anytime you go out to a different module, we've got this here, call ext, so call external. Meaning we're calling maps find, which is interesting because we don't actually call that in here. We say map.fetch. But if you look at the docs for map.fetch, it'll say inlined by the compiler. So there's a whole bunch of stuff when you're looking through the Elixir documents or documentation. If a function says inline by compiler, that's good because it'll turn it into something like this, which is faster because it means just calling the raw Erlang code instead of having to say, okay, here's an Elixir library that wraps the Erlang code and it's going to call that. And there's a few extra steps along the way to make it work. Got a few other things in here. So in these things, when we do our find, the first thing we do with that, so when we say find, this is a fetch here. So that there, see, inlined by the compiler. It'll turn it into map find. Then it grabs a result of that and it does a match. It's either going to be an okay and result if we've seen that value before and we can just return it without having to recalculate it, or error if we haven't seen it and we need to do the calculation. Looking in here, that's what this thing here is. So we've got test is tuple. This is a low-level instruction again. The tests are kind of interesting. I won't go through all the stuff here. There's a lot of noise in there. But basically, it's saying that it's going to be a tuple here. I forget what these things are. Yeah, exactly what all these things here mean. I'm still kind of sort of figuring out and learning about that. But the important bit is that if it works, this will just keep going down through these instructions here. If it fails, so if it's false, if it's not that thing, then we do the jump. So that's how you do an if or a case or a switch or whatever. You don't have like an if with two separate blocks. You have like a do a test. If it works, you just keep going. If it fails, then you jump to wherever this says. So in the case where it works, we're going to grab the tuple element at position 1, which is our result. We're going to put tuple 2, which creates a tuple, then we return that thing. In the case where it didn't match, then we have to do the work. And this is where it's kind of similar. So we're doing a minus built-in function again. Here it's doing another call. It's doing like a fib memo, calling that again. And then it's sort of doing a bit of housekeeping, just keeping track of registers and things. But you can see here, that's the plus of the other one. Then it's doing like a test to see if it's a map. And then we're putting it in the map if it's there, I think. That's what this is saying. And at the end, we're ultimately returning it. And this one here is interesting. So we've got a thing here for bad map, which is saying, where does that come from? That's there. So I think that one is at line 7. These don't match up at all. I think there's something inside here. It's going to be doing a check to make sure that it can actually put that in there. So when you pass in that memo into map.put, it's going to be a test in there to make sure it is actually a map, is what this is saying. So we're saying make sure this thing is actually a map. If it's not a map, then go to here. We get an error saying Erlang error, bad map. And yeah, so it's just like a really quick, very, very, very quick overview of how this stuff works. If you want to dig more into this, there's this Google Beam book. And you'll find this, it's like an open source document. This is where pretty much all the stuff that I figured out about this comes from. And this goes into a huge amount of detail about all the stuff, like the internal workings of how the Erlang VM runs. It's just heaps of stuff in there. It's not all complete. There's a whole bunch of sections that are just placeholders, but the stuff that is there is really, really good. So it's like all the, if you want to sort of dig into what the operations look like, or the internal to how memory or scheduling works, this is kind of the best source for it. Apart from that, it's just reading the Erlang source code, which is kind of clunky, but once you've looked through it a bit, it's not too hard to find your way around. Yeah, so that was it. That was just a very quick overview of that. this thing here for like doing that disassembly, if you're interested in that, I've got that on my GitHub. I haven't published it on Hex yet, but I probably will when I've cleaned it up, but it's just very rough at the moment. But you can probably go there, MadLab, Keynote Disassem, and have a play with that if you really want to. It's literally just a matter of, in Livebook, you just need to do something like that to pull it in. I've got it pointing at my local directory here, but you can point it at GitHub. That works just the same. Yeah, and then once you got that, you can just chuck that in and do like that there, and then that'll kind of give you the output. So I'm going to clean this up and make it a bit more interactive and nicer formatting and whatnot, but that's, yeah, the general idea is to make it easier to kind of understand these things and work with them. Cool. Any questions or anything?
Curious if, like I noticed you used map.fetch, and you said that it was inlined by the compiler. Similarly, is it also inlined with like a map.get, or is it slightly worse?
Yeah, map.get I think is not. Yeah, because I think it's doing some extra work in there.
Because it has like, I think it falls back to the nil.
Yeah, I think that is it. Yeah. So it looks at a map. If you Google it, it'll say in the docs, and you can look at the source code and figure it out pretty quick as well. So if you say, yeah, I think the nil handling is why it's not, and you can check this out here as well. And you can see there, it's actually, yeah, I mean, it's got Elixir code that's written in there. So it's having to do a bit of work there.
So I'm new to this stuff. So correct me if I'm wrong. So Beam is the virtual machine that Elixir runs.
Yeah. So yeah, I should have explained that at the start. Sorry. Yeah. So that's the name of the virtual machine. So when you run Elixir, you're running it on top of Erlang, and Erlang is running on top of the Beam virtual machine. Which
then the actual question is, can you get the registry of that virtual machine, not the 0, 1, 2, the actual address of the registry?
You mean of the registers?
Yeah.
Probably. It does a whole bunch of extra steps as well. So the bytecode you see from those files, it'll have some extra transformations when it gets loaded into the virtual machine. So that's pretty close to what it runs, but it'll kind of run it and do a whole bunch of other transforms at compile time. That's kind of some of that's based on the architecture of the CPU you're running on and whatnot. So it's not a one-to-one. Like, there probably is a way to get it. And I'm pretty sure in the underlying API, like it's all written in C. So if you go into the C API, there's probably ways to do that. In like the actual bytecode itself, not so much, because it's sort of at a fairly abstract. It's higher level than that.
Yeah. So because it uses this symbol, and then you usually use this symbol, that means you get closer to machine, like machine code.
Yeah.
But the way that I see it, it's more like closer to programming.
Yeah, it's disassembled the bytecode in the file. So when you compile Elixir, it'll compile it into a .beam file, and so that's what that binary is on this one here. So that's kind of giving you that there. And it's just saying it's the Beam, this module here, which is what this is all using under the hood. It just goes through and it basically just passes those bytecodes in there and then produces this output here. You see, so yeah, it's not the assembly. I think there are ways to do that, because yeah, there are ways to look at how it's ultimately transformed everything into the low-level instructions, and it's got some of it gets just-in-time compiled as well, so it gets more complicated.
All right, thanks.
Cool. Anything else? All right. Well, thank you.